Great, welcome to More Study Guides with Mrs. Durham. Now we're going to talk about the Case 21 Semester 1 Study Guide. The first thing I want you to do is put your government name up here and what class you take this class. The second thing I want you to do at the top here is write test grade due on December 15th, because that's the day you take your test. You need to turn it in either on the 15th or the 16th, depending upon what day you have science and how the schedule looks. I don't know what the bell schedule is going to look like, but I'm going to say it needs to be turned in by the 16th at the absolute latest, or else you're going to get a 0 on a test grade, and I don't think many of y'all can afford that. All right, the first thing we're going to look at is this table. This table shows the periods of geologic time during the Paleozoic era. What can be concluded from this table? Let's look. We have era, periods, amount of time, and then some distinct features. All right, the first answer, and I didn't do a very good job of separating these, my apologies. During the Paleozoic era, small mammals and birds evolved. During the Paleozoic era, small mammals. Do we see anything over here about small animals? Don't see anything about mammals at all. Okay, can't be that. All right, during the Paleozoic era, Paleozoic, all life forms were simple and unicellular. That means they have one cell. Think back to 6th grade. You're multicellular. Fish are multicellular. Nope, that's not factual. All right. During the Paleozoic era, reptiles were most abundant organisms. This really doesn't tell me anything about who's abundant, and we don't see reptiles till like way up here, and like we had all these other critters, so I don't think that's right either. During the Paleozoic era, evidence of diversity of life from ocean life to land. Yes, now that makes sense because we're talking about amphibians, marine animals, coral, forest, conifers, which is like pine trees, sharks. So this is giving me diversity of life vibes. And when you see the words diversity of life, it is almost always going to be that answer. For the next one, based on the fossils contained in the diagram, what can you infer about the evolution of this animal? List at least 3 things. So it's a little hard to tell, but this is a terrestrial dinosaur. This is probably something that lived on land and in water, and these are all underwater and starting to look more like dolphins. So 3 things that I can tell from this is that this animal in particular, they made small changes over time, right? Because we're starting on the land and we're ending up looking like a dolphin down here with flippers. We can also say that we went from land to water. And the number of limbs changed. We started with 4 legs looking more flippery, all 4 flippers. Then we're down to like 2 flippers and like this cool looking tail, bigger flippers and a skinnier tail, and then something like in the middle. I know it's really hard to tell on your paper. I don't know if you can tell maybe on this one a little better. But the number of limbs change. All right, complete a topography vocabulary chart. Oh my gosh, look at that. Showed up right there. Let's do it again. Topography. We have weathering, which is destructive. We have erosion, which is destructive. Mind you, we're using all the words from here. We have deposition, which is constructive. And there's 2 types of weathering. We have chemical. And remember, the M in chemical means changing molecules. It's a brand new substance. And then physical. which is just making things into smaller bits. Alright, moving on. Using the terms found in the table below, label the above diagram and give a description of the terms in the table. Alright, the first thing I'm going to do is write my vocabulary so that I can use it to solve. Alright, convection current. We're going to say less dense. Oops. Magma floats more dense magma sinks. And remember, this is going to be the hot stuff up here, and this is going to be the cold stuff here. And that it powers plate tectonics. Now, right away, I see something that looks like it's a cycle. Remember that convection currents are a cycling of heat. Alright, so we're going to put convection current there. Divergent. Remember, divergent means we're going away from each other. This is going to be plates. Moving away, and this makes new plate. If I look up here, I see kind of like two arrows coming away here. See how this arrow's here? This arrow's kind of covered up a little. This is divergent. The divergent boundary. Alright, then we have convergent. Plates move. They move towards each other. And this recycles plate. And I can see there might be multiple places where there's a convergent boundary, but specifically we see this plate's going under, so we know this has to be a convergent boundary here. There's another place you could have put this, but I like it there. Seafloor spreading. This is the separation of oceanic plate moving, whoops, made a mistake, hold on, knew it as soon as I wrote it. Not moving, it's making. I mean, it is moving, but making new plate. Alright, a subduction zone. This is plate going under another plate. And being recycled or destroyed. Now, I can see that subduction's happening in a couple places, but we're going to put it here. This is the subduction zone. Alright, the lithosphere. It's a rocky layer. of Earth's crust. It's separated into plates. Alright, I'm just going to say it's this here. It's kind of hard to tell, but because this is thicker and more dense, we're going to say it's more of a solid and this is a liquid. So this is the lithosphere. Alright, the asthenosphere. Oh no, is my pen going bad? Liquid upper mantle where plates float. The asthenosphere, I think I'm going to put it here. Alright, then we have a mid-ocean ridge. This only happens at the separation of oceanic plates. It makes new plates. So I would like to put that maybe here. Did we put seafloor spreading on here already? We missed it. Okay, look, here's what I'm going to do. We're going to put mid-ocean ridge. But this is the location of seafloor spreading. Alright, and then we have a trench. Subduction zone between continental, subduction zone between continental crust and oceanic crust. We're going to say that this is a trench here, because that's kind of like this area here is the trench. And this is an oceanic plate because it's super dense. And remember that continental plate is like cotton candy. It's not as dense and it's much fluffier. Oceanic plate is more like a brownie where it's really thick and dense. Oceanic plate will always go under continental plate, and if two oceanic plates converge, the oldest is going to go under. Alright, oh no, it's that rock cycle again. Good thing you have your handy dandy cheat sheet. Look at that. We can use that to help us. First thing I want you to do is label this magma. It's a liquid. You could even shade it orange or yellow if you have your colored pencils today. This is sediment. And up here is igneous rock. Now, I know this by heart, but if you didn't, you could practice using these words down here. And you could take a blank sheet of paper, draw out your rocks first and your arrows, and then try to just use these words down here. to help fill it in. That would be a really smart study tool there. All right, down here is going to be sedimentary rock. I know that because sediment has to become sedimentary rock. You know, it's kind of logical. This is going to be metamorphic rock because it's wavy. All right, now we just have to fill in our actions. Starting with magma. It needs to cool to become a solid, or it needs to melt to become a liquid magma again. For igneous rock, for it to become sediment, it has to undergo weathering and erosion. All right. Again, for sedimentary rock to become sediment, it has to undergo weathering and erosion. All right, and for sediment to become sedimentary rock, it has to undergo compaction and cementation. All right, sedimentary rock can become metamorphic rock only through heat and pressure. All right, for metamorphic rock to become sediment, it has to undergo weathering and erosion. For metamorphic rock, for igneous rock to become metamorphic, it has to undergo heat and pressure. And for metamorphic rock to become magma, it has to melt. We did it. We used all the words down here to complete our chart. Let's see if I can get this to focus. There we go. All right. Fossils are found in what type of rock? Well, because bones often end up as sediment, the only thing they can form in is sedimentary rock. All right, list the 4 pieces of different evidence that best supports the continental drift theory. 1. Continental fit. That's like where South America looks like it was snuggling up with Africa at some point. Then we have glacial evidence. Where glaciers have scraped over entire continents and the scratch marks match up. We have fossil evidence. Things like Glossopteris can be found on all 7 continents, even though it's a tropical fern, because at some point all the continents had to be tropical. And then mountain ranges. The Appalachian Mountains are a part of another mountain system that is found in Europe, the oldest mountains in the world. Oh, my hand's starting to hurt. One moment. All right. Name the geologist known for this theory, continental drift. We see the D there, and we have a D in Alfred Wegener. What is the theory? plates used to be, so what is the theory? Plates used to be stuck together and later moved. And remember, when they were stuck together, it was called Pangea. Alright, seafloor spreading. It's got 2 S's in it, and those are for Harry Hess. New ocean crust made at, and his theory is where new ocean crust is made at mid-ocean ridges. Alright, plate tectonics is a combination of these 2 theories put together. And it's that plate movements, or the Earth's crust, is broken up into plates. Plates movement is driven by convection currents. Alright. Oh no, this chart looks very familiar. It's kind of like a slightly more advanced version of what we drew up here. So we're halfway there. We're just going to think about it a little deeper. So, we have a plate boundary, land versus land. Remember that continental crust is big and fluffy, and the oceanic crust is thin and dense. So convergent means they're going together. Alright, feature or event. We see uplift with this. And we see mountains. This is why Mount Everest is still growing, is because the plates are smushing together and making the mountain go up. Convergent, land versus ocean. This is going to be a big fluffy piece of crust versus like a brownie piece of crust. Whoops, I did the wrong one. My bad. Land versus ocean, right? The movement is convergent, where it goes together. And the things that we see here is subduction of oceanic crust, meaning the dense crust goes under. Actually, let's change this a little bit too. I want to change these arrows. So sorry. Let's do it like this. If it's land versus land, we're going up because we're golden. If it's land versus ocean, we know that someone is going down. Let's draw it like that. All right, so we have subduction of oceanic crust. We see trenches, and we see volcanoes. It would be really helpful to put these on flashcards and then study them that way and like quiz yourself. Convergent, land versus land. You should be able to like do the hand motions that's going up and then say that it's uplift in mountains. And if you flip it over and it's wrong, you put it in the wrong pile. And then when you're done with the whole pile, you just do your wrong pile over and over again until it's right. All right. Convergent, ocean versus ocean. It's 2 dense pieces going together. And what happens here is that the oldest ocean plate is going to go under. So here we see the oldest is destroyed or recycled. And we get a trench. All right, Divergent land versus land. Remember, this is big fluffy pieces. They're going their separate ways. New crust gets made here. It makes something called a rift valley. If you've ever seen The Lion King, where Mufasa looks at Simba and he goes, Simba, everything the sun touches is yours except for that dark place over there, and that's Memphis. That's actually a rift valley in Africa. One day that will all be a giant filled-in ocean. Not while we're around, but eventually. All right, divergent ocean versus ocean. New crust is made. We can't make a new ocean because we already are the ocean. But we get a mid-ocean ridge. For a transform boundary, we get this side-to-side movement like this. And this generates earthquakes. All right, place these layers in order from youngest to oldest. The first thing I want you to notice is that E is a fault line, which means we have unconformity. Remember, if you conform to something, you're going to look like it. If you're unconform, it means there's two things that don't look the same. Fault lines only happen during earthquake events. All right, so what's happened here is something's caused that earthquake, and this would be all this igneous rock that has shot up out of the ground. So D would be the youngest here, and it is extrusive igneous. It's extrusive because it came out up here. The next one would be A, then B, then pour C down here. All right, types of plate boundaries. You're going to identify the following terms with letters on the diagram above, but we have no letters, so I guess we need to label them. All right, the first thing I'm going to do, if you notice our continental crust is big and fluffy, our oceanic crust is thin and dense. The first thing I'm going to do is label these. And I'm going to add another one. I'm going to write the word uplift and put G. All right, for A, that is going to be here. Remember, this is oceanic plate and it's diverging, and that's where seafloor spreading happens. This location is A. My next location, B, would be a trench, and trenches only happen at convergent boundaries. This area here is going to be a trench. For C, a divergent boundary is plates that are going in opposite directions, and that can only be happening here. For D, a subduction zone, that's an area where plate has to be going under another plate. That's happening here. All right, the subduction zone. Oh, we already did subduction zone. My apologies. The mid-ocean ridge. That is happening at the seafloor spread location, so we have to put an E here. All right, F, a convergent boundary. I really like this one here because it's very easy to see. In uplift, we can see that mountains are being formed, so this location would be G. Where are the oldest and newest rocks located on the seafloor? The oldest rocks are located at the edge of the plate where old crust gets recycled. The newest rock is at the mid-ocean ridge. Where new crust is made. All right, what is the difference between chemical and mechanical weathering? Remember, chemical has that M in there for molecule, and it's rearranging the molecules. For physical, it makes smaller particles. But the molecules stay the same. Alright, we're going to make definitions and examples for each. So remember, chemical weathering, a new substance is made. An example of that would be like acid rain dissolving a rock. Or mechanical weathering, smaller pieces of rock are made, right? An example of that would be like smashing rocks to make gravel. Alright, the law of blank is used to predict the relative age of layers. That's going to be the law of superposition. We can get the exact date of rocks through something called carbon dating. That has to be done in a lab. All right, what are 3 characteristics of index fossils? They have to be widespread, like cockroaches, right? They're widespread. They have to be plentiful, which means like lots of them. And they have to live for a short time. That's why something like a crocodile is a bad index fossil, because they've been around for millions of years. All right, what type of technology is used for the following disasters? We have earthquakes and volcanoes, and you're going to use a seismograph to predict those. For a tornado or hurricane, you would use satellites or Doppler radar. A region experiences a very explosive volcanic eruption from a single volcano. What change will likely occur in the region immediately after the eruption that would impact organisms? A, an earthquake will occur due to lava flows along the plate boundary. That doesn't make any sense. B, plant-eating animals will thrive due to fertile soil formed from volcanic ash. Well, maybe later, but we're talking about immediate outcomes. The humidity of the region will increase due to blocking of the sunlight. We haven't said anything about that, so that doesn't make sense either. I hope D makes sense. The daytime temperature of the region will decrease due to blocking the sunlight. That makes more sense. If there's a whole bunch of volcanic ash in the air, the sun cannot hit the ground, and things are not going to grow, and it's going to get cold. So that sounds accurate. All right, 13. All of the following statements are true about the meteor impact at the end of the Cretaceous period, except... Okay, so this might be something about that KT boundary. Remember, the KT boundary is that thick layer of ash that shows up in the rock history, and it's from the big impact at the end of the Cretaceous. All right, so let's figure out which one doesn't make sense. A large amount of dust blocked sunlight from Earth. That's accurate because we said it was a huge, thing that shows up in rock history. B, the Earth became cold and dark for several months. It probably did happen because, again, a bunch of volcanic ash. Or not volcanic, I'm sorry. A bunch of meteorite dust went everywhere. All right, dinosaurs started to become extinct due to lack of food and sunlight. Well, that's probably what would happen if there's a whole bunch of ash all over the planet. All right, and D, large quantities of nitric acid were produced. We never said anything about that. I didn't teach you about that. It has to be D. All right, natural resources. Define both words and give an example of each. Is it on the next page, maybe? Let's look. Look at that. It's on the next page. All right. My hands are getting tired, so I'm going to let you look on my paper for a second. All right. Renewable. These are things that can be easily replaced in your lifetime. Renewable resources are things like solar, wind, water, biomass. I have that word here. All right, non-renewable, they cannot be replaced in your lifetime. And an example that would be gas, oil, petroleum, natural gas. Go ahead and pause me if I'm going too quick. All right. Most countries are moving away from using non-renewable energy sources because if we increase CO2, we increase global temperatures. And what are the effects of deforestation? Remember that plants are the lungs of our planet, and if we start killing them off, we're going to increase the amount of CO2 in the atmosphere. It also increases erosion. It's going to decrease the amount of usable oxygen we have. All right, with the lamp on, student records the temperature of each sample every minute for 10 minutes before switching the lamp off and measuring the temperature for an additional 10 minutes. What is the purpose of the student's investigation? The correct answer here is B, to show the color of substances and their ability to absorb light. Remember that black over here absorbs all light, and something like water is just going to transmit or reflect, right? If absorbing light, it's also going to absorb the heat energy with it. All right, justify your answer. Well, we just did. Black absorbs all wavelengths of light and white reflects. All right. A student investigates how materials collect heat to cook food using 4 identical solar ovens lined with 4 different materials. A solar oven is like a pizza box, and you can line it with different stuff, and it'll absorb all the heat from the sun. You can like bake cookies in it. Maybe we could do that at the end of the year. We'll revisit that later. Somebody remind me. All right, the table shows the starting temperatures and final temperatures of the materials after 6 hours in the sunlight. So we have like the mass of material. We used aluminum, brass, copper, and iron. The area of the material, I guess, was like 30 square feet maybe. And then the starting temperature, I'm going to assume, is Celsius, and the final temperature is over here. So let's just like make this Celsius to make Mrs. Durham happy. And look, if we look over here, we can see the aluminum got up to 74, the brass got up to 142, the copper was only 141, the iron got up to 123. Which material, oh no, captures the most thermal energy from sunlight in 6 hours? Well, if we look here, we can see that this has the highest number, and if we go over here, we see brass, and we've selected brass as the correct answer. Okay. Now we are going to fill out a chart. About the different types of clean energy sources. So, we have different types of energy. We have solar, wind, nuclear, and we're going to think about like natural gas, fossil fuels, and we're going to lump them all together. All right, for solar. Where is it used? It can be used almost anywhere. An advantage is that sunlight is unlimited. The sun comes up every day, I hope. Which means we have a constant access to free power, baby. Disadvantages, if you live somewhere like the Pacific Northwest where it rains every day, like if you've seen the Twilight movies and everything's gray and misty, it's kind of hard for solar energy to like do its thing to its full potential there. And if you live somewhere like Barrow, Alaska, that has 27 days of night every year, those 27 days you might need to have an alternative energy source. How does it make energy? It collects ultraviolet waves and it converts it to energy. Solar panels are almost always black, and black absorbs all colors and the additional heat. For wind energy, just ignore this, ignore that, don't look at that, don't draw this, don't draw that. Okay. Wind energy, we use it in flatlands and coastal regions. It's mostly constant, especially if you live somewhere near the ocean. And it's sustainable. A disadvantage is that you could have like days where there's no wind. Also, it's like not always great for the birds, but you know, the strong need to survive. And how does it make energy? Well, the wind turns a turbine to generate energy with a generator. Nuclear. We can outfit old coal power plants to do nuclear energy. It is really cheap. We have stockpiles of nuclear energy all over the place in the United States. It's just not being used. A disadvantage is that you can have nuclear waste, and we have a couple dumb laws that prevent us from re-enriching plutonium back into uranium and running it through the plant again, even though the plant can do it. And it generates large amounts of energy. But like, also, what do we do with all the nuclear waste? Because I've seen enough superhero movies to know that's a bad idea, to just have that stuff laying around. All right, fossil fuels. These are things like coal, oil, gas. They get called natural gas, natural fuels. The problem with that is that it sounds safe, and it's really not. Where is it used? It's used absolutely anywhere and everywhere. It's very cheap because we already have all the infrastructure in place to make it. A disadvantage is that it increases CO2 emissions, which increases global warming. And there's only so much of it. It's finite. Finite. There we go. Coal makes electricity. Oil we typically use for transportation. Gas we also use for transportation. You can even have cars that run on natural gas these days. All right. Determine if the following is either harmful or beneficial to groundwater. If we increase the amount of precipitation during during the summer or spring, oh my goodness, start over. I got tongue-tied. If we increase the amount of precipitation in the spring, it is beneficial. If we have more rain, we get more groundwater because more is going to matriculate in. If we increase human population in an area, it's going to be harmful. You can think about the Dust Bowl. That happened during the Great Depression. It's because all of the water reserves and the water table got used up. If we increase in the summer temperatures, which leads to more evaporation, that would be harmful because less water is going to make it into the water table. Precipitation infiltrates in the ground, accumulates. That's beneficial to groundwater because it's replenishing the groundwater supply. If precipitation freezes and thaws in a cycle, forming large ice lumps, that is beneficial because that can act as a temporary water reserve, and when it melts, it gets added back into the water supply. Okay, this next one. Oh no, don't look. We have this really cool chart. It's got multiple axes. Let's look. It's comparing global warming temperatures in degrees Celsius, that's the black, atmospheric CO2, which is the blue, sunspot activity, so that's going to be like the sun having like extra electromagnetic waves, and then the Antarctic ice core CO2, which is like how much CO2 is being stored in Antarctica. All right, global warming temperature in Celsius is on this axis. We have atmospheric CO2 on this axis, and then we have the years down here. And we notice a trend. What is our slope saying here? Our slope is going up, so we're seeing an increase in atmospheric carbon dioxide, and we're also seeing an increase in temperature. What inference can be used between the relationship of CO2 and global temperatures? Oh my goodness, we've already figured this out just by reading our graph. As CO2 emissions increase, global temperature increases. Look at the big black bar. Global warming temperature has increased substantially. Okay. Or the next one. Is a scenario constructive or destructive? Chalk dropped into a jar of vinegar. Remember, constructive breaks down plate. And destructive builds up. Oh! Just don't tell Miss Pennington. Do not tell Miss Pennington. Oh my God, she's going to yell at me that I said that. I did it backwards. Okay, constructive builds up plate. And destructive breaks down plate. And when we say plate, we mean like any rock, okay? Or giant lithospheric plate. It's all the same. All right, chalk dropped into a jar of vinegar. That is destructive, and specifically we can say that's a chemical change, right? Because the vinegar is going to dissolve the chalk. That's a chemical process. All right, the Colorado River carving out the Grand Canyon, that is destructive. Out saying it's carving. Oh, that says craving. Golly. C-A-R-V-I-N-G. It should say carving out the Grand Canyon. That's destructive. The Mississippi River deposits debris from the delta. Remember deposition? If we go back over here to our chart, we look, deposition is constructive. It has the word deposit in it. It's constructive. Alright, old rock being recycled at a subduction zone is destructive because it's breaking down a recycling plate. The deposition of sediment is always constructive. The process of seafloor spreading, pushing plates to the side while magma erupts to form a mid-ocean ridge, is constructive. At a divergent boundary, land versus land, a rift valley is created, and that is constructive because we're making new plate. Next, we're going to sort the following characteristics into two categories, some belonging in both. We're going to have electromagnetic waves and mechanical waves. Oh no, I have to go teach. Okay, so we're going to sort the following terms into each of these categories. Some items may belong in both. So we have electromagnetic waves and mechanical waves. Remember, you have your cheat sheet from the wave section that you can use for this. Alright, let's look at the first item. It is transverse wave. Reminder that electromagnetic waves can only be transverse. But mechanical waves can also have transverse waves. Remember that they show up as water waves. Light is specifically an electromagnetic wave. Heat is also an electromagnetic wave. Infrared, if you check your cheat sheet that you should hopefully have memorized by now, IR shows up on the cheat sheet. Then we have ultraviolet. You should stop falling asleep in class. Alright, ultraviolet. Then we have gamma. And I didn't even have to memorize all these individually, I just memorized this quick chart. Water waves, we know those are mechanical. Seismic waves, those are going to be the waves associated with earthquakes, are also mechanical. Sound waves are mechanical. To make our little division here. Carries information over long distances. That has to be an electromagnetic wave because those are the ones we use for communication. Carries energy. That's going to be both types of waves. Travels through matter. That could be both. Travels through empty space. Only electromagnetic waves can do that. Requires a medium. That's mechanical waves. Alright, this question keeps showing up over and over again. A wave energy device moves back and forth with the motion of a wave. It produces more energy if more waves pass in a certain period. Which property of waves does the wave energy device use the most? Well, if it's moving back and forth, that's going to deal with amplitude or frequency. Remember that amplitude is how high a wave is and the frequency is how often it's happening. In this instance, it has to be frequency. Answer the following question using the table. Our table is here. We have a medium, which is like going to be a solid, a liquid, or a gas. Possibly nothing. A type of wave, a sound wave, and a light wave. And we should be able to answer questions. Alright, sound waves move fastest in. So we have speed in meters per second. So we're going to look for the biggest number. In this case, 5,640 meters per second, and that's going to be glass. Sound waves move slowest in. Nothing. Remember, sound waves cannot move in a vacuum because they need another particle to bump into to transmit their information. Light waves move fastest in. If we look at our numbers, it looks like 300 million is the highest number. Nothing, or the vacuum of space. And they move slowest in. If we look here again, glass. So it is the exact opposite of sound. For the next section, you're going to circle the wave that has the highest frequency. Remember, frequency is just the number of up-downs per second. And we want the highest frequency. It's going to have the most up-downs per second, so it has to be this one. For this one, circle the wave that has the highest wavelength. Remember, if frequency increases, then wavelength has to decrease. So if we have a high frequency, we have a short wavelength, and it has to be this one. Low frequency is a lower wavelength. Fill in the missing word as decrease, increase, and draw what the wave looks like. If we increase wavelength, we have to decrease frequency. And I'm going to draw it like this. If I decrease the wavelength, I can increase the frequency. Alright, what are the waves that transmit information and what technology is used to transmit them? We use electromagnetic waves for this. We use technology like satellites, radio towers, cell phones, and Wi-Fi routers to get the signal out. Use the electromagnetic spectrum, or EMS, below to answer the following questions. Alright, so we have the radiation type, and we have the wavelength in meters. Which wave has the lowest frequency and the longest wavelength? Well, if we look here, this has a pretty low frequency of only one up-down. And the answer is radio. Which wave has the highest frequency and the shortest wavelength? Well, if we look up here at gamma, it has the most up-downs per second. So that is the shortest wavelength and highest frequency. Which wave on the EMS can be seen by humans? And that is the visible light spectrum. Sometimes we call him by his government name, Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Those are in order by wavelength. Which wave is used to treat cancer and tumors? That's going to be gamma. On a bad day, it could give you cancer. We'll talk about that next semester. And ultraviolet waves have a higher frequency compared to microwaves. we look here, we have a whole bunch of up-downs per second. If we look at the microwaves, we only have one. A light wave can either blank, whoops, did I miss something? I think I accidentally deleted something. No, I didn't. There it is. Okay, let's talk about it. So, light waves can either transmit, refract, reflect, or absorb. Remember, transmit is when it's going through. Refract is when it's going through and coming out and something about the wave has changed. Reflect is when it bounces off. And absorb means it's just staying put in a substance, like when you absorb the sound waves in Mrs. Durham's class. Describe what is happening to the light wave when it interacts with the following colors. If something is black, it's absorbing all the wavelengths of light. If something is blue, it's absorbing Roy-G-Biv. Oh, not quite. It's absorbing red, orange, yellow, green, indigo, and violet, but it's reflecting blue, and that's why you see it as blue. If something is white, it's reflecting all wavelengths of light back to your eyeball. And if something is orange, it's absorbing red, yellow, green, blue, indigo, and violet, but it's reflecting orange. This is why we can't have nice things. I'm waiting for y'all to collectively figure out how this is going to go. Fill out the table of wave behavior and draw a picture of how the wave moves. So we have a wave behavior description and a drawing of a wave. For transmission, this is energy going through a substance, and I drew it as going through a piece of glass. For reflection, this is energy bouncing off a substance, like an echo or light or sound. Refraction is energy scattered by a substance. This is going to be something like a prism where white light hits it and it gets cut into its individual colors, ROYGBIV. Alright, if we look at the left, we have some pan flutes, and we can tell that we have a little pipe and we have big pipes. Remember, when we talked about this, the little pipes give off a high frequency note, and the long pipes are going to give off a low frequency note, and this is true for almost every single instrument. If it's a guitar, if it's a marimba, if it's a piano, it's all the same. So the longer the pipe, the lower the frequency. And what does that mean about the pitch of the note? It means that it has a long wavelength and a low pitch. The shorter the pipe, the higher the frequency. What does that mean for the wavelength and the pitch? It means it has a shorter wavelength and a higher pitch. How can the resonance of a handmade instrument change? There's really like 3 things that we could do. We could change the material that it's made out of. If it's something like a guitar, you can change the thickness of the string. And you could change how much tension is on a string. So if you pull it really tight, it's going to be high. If you leave it loose, it's going to be low. For a large amplitude, sound is going to be loud. So large amplitude, we have a large sound. That just means the distance from 0 is really big. Alright, with a small amplitude, you're going to have a soft sound. That means the distance from 0 is very small. Based on the provided charts, determine what materials EM waves and sound waves move best and worst through. So we have a couple of charts at the bottom we're going to go over. Okay, so based on the charts, we're going to determine what materials EM waves and sound waves move best and worst through. So if this is the speed of sound, this is definitely going to be mechanical, right? And we know that mechanical waves need a medium. First thing I noticed right away is that it says vacuum, and that's 0 because it couldn't travel through the medium because there's nothing there. Mechanical waves need other particles to bounce into to send their information or energy. So EM waves are over here. Remember, light is an EM wave. EM waves travel best through, if we look through here, a vacuum, which is the opposite of mechanical. So the vacuum of space, or nothing, is the other thing you could write. And they travel worse through, if we look on our list, steel. For sound waves, we can see they move best through diamond and worse through a vacuum. They move well through diamond because it is a very dense material. The denser the material, the easier a mechanical wave is able to move through. Remember, this is a test grade. You need to turn it in by the 16th or it's a 0 because I'm getting work picked up daily from school. Any questions or concerns, feel free to email me or message me on school status. Good luck on your exam, guys.